So, thank you, the organizers, and thank you, Professor Toshanta Panegre, sir, for organizing this wonderful workshop and conference. Today, I am going to give my presentation talk on the persistence of quantum triality relation in open eight-dimensional system. So, the motivation of this work is like the age-old wave particle duality. So we know that everyone here knows from the physics background that wave particle duality is one of the most fundamental and fascinating feature in quantum mechanics. In the context of interferometry, we characterize two quantities here. One is visibility and another is predictability. Visibility quantifies the wave nature of the of the system, and predictability defines or quantifies the particle nature of the system. So we here encounter with another term, that is quanton. Quanton is typically one system that can be electron, that can be photon, that can be light, whatever, that exhibit wave and particle nature. This in this single term, it is called quanton. So what happened? Traditionally, complementarity is coming from the p square plus v square, that is visibility square, and predictability square is less than equals to 1. This is for the when the quantum does not interact with the detector or anything. In realistic scenario, what happened? The quantum cannot be an isolated system. It interacts with the path marker or the detector, and while interacting with the path marker or detector, it generates some correlations, and this correlation or interaction gives rise to the quantum detector entanglement. When we include this entanglement into our framework, like the traditional complementarity, this inequality becomes an exact identity. This is a relation v square plus p square plus epsilon square equals to 1. Now this is the quantum triality relation. Now the exact question after comes in our mind, that whether this triality relation remain robust and valid when this system is exposed to the environmental noise. So next, before going to the details of our work, we will discuss the evolution of the quantum complementarity. This is an 300-400 years age old problems. So this is a long time story I am going to tell in a nutshell. I think more or less everyone knows the story, but I just want to recapitulate the things. In 1678, Christian Huygens proposed that light behaves as a wave. His wave theory successfully explained phenomena such as reflection and refraction, and later become the foundation for the understanding of interference. However, this was changed by Isaac Newton. Newton, in his book, I think Optics, proposed one theory, that is corpuscular theory, in 1704. He told that light consists of teeny particles or corpuscles. Because of Newton's immense scientific influence and his immense contribution, the particle picture dominated physics for almost a century. It was the debate was going on and on. After that, in 1801, almost 1 century later, Thomas Young performed his famous double slit experiment. He observed that if one use two slit alternating bright and dark fringes on a screen, after light passes through the narrow slit, these interference fringes could only be explained if light behaved as a wave. Young's experiment therefore provided convincing experimental evidence for the wave nature of light. Now, Again 100th century. In 1905, Albert Einstein explained the photoelectric effect by proposing that light is composed of discrete packets of energy called photons. This again revived the particle description of light. Suddenly, light can exhibit both wave-like nature and particle-like characteristics, depending the performance, what performance we are going to observe. Now, this contradiction is going on until 1928. Bohr described the complementary principle. He described that wave and particle behaviors are not contradictory. Rather, they are complementary aspect of the quantum system. If we perform experiment designed to observe the interference, we lost the information about which path the particle is following. Conversely, if we want to focus on the path the system is following, Bohr's principle beautifully explained this behavior, but it remained a qualitative idea and did not provide a mathematical measure for this scenario. Again, I can also remind you the Heisenberg uncertainty principle. This is kind of supporting Bohr's statement, that is, position and momentum cannot be determined together. That is the uncertainty. Kind of this is supporting the Bohr's statement. Now we will come to the latter part of this century, 1988. Greenberger and Yasin introduced the first quantitative wave-particle duality relation, that is p square plus v square less than equals to 1. Here, visibility quantifies the wave nature of the particle by measuring the contrast of the interference fringes, and predictability quantifies our prior knowledge of which path the particle is likely to take. This is like one probabilistic approach. This inequality tells us that wave or particle properties compete with each other. If the visibility is maximum, there is no predictability, it will vanish immediately. Similarly, when predictability is maximum, so when we get the full path knowledge that this path the quantum should follow, then we will have no information about the visibility. And after that, 1996, there is another statement, another works comes into the picture, that is d square plus v square less than equals to 1. D square is the path distinguishability, while predictability depends on how the quantum state is prepared. It quantifies the path actually be distinguished using a detector or measurement apparatus. So after that also, in 2017, after that, like in this century, Professor Qureshi investigated multipath interferometers. He demonstrated that when a quantum becomes correlated with the path detector, part of the information leaves the quantum and it is stored in the detector. Consequently, wave and particle properties alone are no longer sufficient to describe the complete physics. Another in 2020, another conceptually advanced thing comes when Basso and Mazzario introduced the framework of complete complementary relations. They showed that the realistic quantum system, the missing information, especially the mixed state, the missing information is stored in the quantum correlations with other subsystem. Their work emphasized the complementary must include correlations in order to provide a complete description, the path and detector correlations. Now, based on these developments, Roy and collaborators, Professor Panigrahi, Professor Qureshi, all are included, Nitish, all are included. They are from our group. They introduced the concept of wave particles entanglement triality for arbitrary in-path interferometers. They showed that complementary is more naturally expressed as v square plus p square plus epsilon square equals to 1. So where the additional quantity epsilon represent the entanglement between the quanton and the path detector. This equation has a very intuitive interpretation. Visibility represents the wave aspect, predictability represents the particle aspect, and entanglement quantifies the information shared with the detector. Nothing is lost. Rather, information is redistributed among these three complementary quantities. Whenever visibility decreases, the information reappears as increased in predictability or increased in entanglement, or a combination of both. This naturally leads to the central question of our work. In realistic quantum technologies, no quantum system is perfectly isolated. Quantum computers, interferometers, quantum communication devices constantly interact with noisy environments, which continuously degrade quantum coherence. So the natural question is, does this triality relation survive when environmental noise is present? Now we'll come to our work, like we'll describe a very little bit of our work. That is the system description. Suppose we'll consider an in-path interferometer coupled to the detector state. This is the path detector. Sorry?
I have a question on the previous slide. When you say
Okay.
that this square plus his visibility square plus predictability square plus entanglement square is equal to 1, and you said these three quantities are complementary to each other. So I have a question that if let's say entanglement changes by a parameter called delta x, do you mean that both V and P will undergo a change of x by delta x by 2? If the net change in entanglement is x, do you mean that V and P will undergo a change of x by 2 and x by 2? How do you mean by complementary? When you say that V, P and epsilon are complementary to each other, can you please explain this thing?
Can you please tell me again, because I cannot hear you properly. Like
Ma'am, I'm asking if the relation is written that in the row at all, the visibility square plus predictability square plus entanglement square is equal to 1. Okay, it's no longer an inequality, it is just an abstract relation. So I'm asking if entanglement undergo a change delta. So do you mean that the predictability and visibility will undergo a change of delta by 2 each? If not, then how these three are complementary to each other?
Okay, I think I understand your question. Like sometimes there is separable cases, then it's separable. But when the suppose the state is separable, there is no entanglement between the path and the detector. So at that case, entanglement is 0. But at that time, what happened? B square plus P square equals to 1. We will discuss this as example in the later cases, how this is distributed when the separable, how the separable state comes into the picture, when the entanglement comes into the picture. Other than the complete entanglement, if you skip the entanglement, you there are some, for separable state it is always that following the duality relation, that is p square plus p square equals to 1, as there is no entanglement. But if you consider the entangled state, but still at that case you don't get the equality, you will get p square plus b square less than 1. So I think you are asking this question.
Yeah, later. Yeah, I will ask this
Otherwise,
question.
okay, otherwise, can you please type? I could not hear properly.
Please go on. Later on, maybe I will ask.
Okay, sure. My slides are shown.
Yes, the slides are visible. Can you maybe?
Okay. So now the description comes like this is the complete state, and this is a coupled state, like combined state. We will use the reduced density matrix to trace out the detector part And the tracing out the detector part, we will have the diagonal terms that will give the path probabilities, and the off diagonal terms that is gives the coherence or simply the visibility. And detector overlap controls the entanglement. Now is our goal is to quantify Vp and epsilon. This is the measures of complementarity. Consider a quantum passing through a multipath interferometer. For an n-dimensional system, visibility is this, predictability is this, and entanglement is this. So we see immediately from the visibility terms, that is visibility terms only engages the off diagonal term, while the predictability has the diagonal terms. And entanglement is the coming from the like you need to calculate individually, like here Eij is the concurrence between the quantum and the path detector. This equation, these three quantities will satisfy this triality relation. This work has been done by this group. And now we have showed for the two-path interferometer system. First, we consider a pure path system pure path state. The quantum can be expressed as a coherent superposition of two paths. This is C1 psi 1 plus C2 psi 2. This is a coherent superposition. Now, as this is not directly combined or composite, we don't have the composite system, we have the density matrix in the path basis. So this is the density matrix. So directly we can get the visibility for C1 squared, C2 squared, and predictability path information, that is P square equals to 1 minus 4 C1 squared, C2 squared. So it follows the duality relation, B squared plus P squared equals to 1. Just add this, you will get 1. As there is no entanglement, so entanglement term is 0. And we can see it also immediately. The here, as it is not a composite system or entangled system, you can write the path state and the detector state as a product state. So there should not be any entanglement. And now we will consider two path system with detector correlation. Now we will
Madam Ramita, I have a question. Normally in a classical approach, if when you are doing 2D interference, like you said that Young's double slit experiment, when you are doing Young's double slit experiment, if you see the beam coming from the slit 1 and slit 2, if they are orthogonal in nature, orthogonal polarization, then the intensity pattern will be visibility is 0. Okay, contrast will be 0. It's uniform pattern because it's just the addition of intensity. Okay, so there the means how you are explaining this visibility. So you mean that the predictability is 1.
When you
how, yes, in classical scenario how this visibility
I can explain the classical cases, like when you have no fringes, at that cases there will be no visibility. Then you will get the complete information about the path, like you will get the predictability as 1. Simultaneously, if you have the contrast fringes, if you have the full information about the visibility or the fringes, then you will get that it is 1. Suppose this is 1. Then you will get the predictability as 0. There will be no information about the path it is following.
But as you said, that visibility deals with the wave nature and the predictability deals with the particle nature. Okay, but
yes.
when I say that the beam coming from slit 1 and slit 2 are orthogonal polarized, then the visibility is 0. So in that case, the beam is still wave in nature. It's not P is equal to 1 doesn't mean that it's
better towards the end of the class question may be good. Let him speak. I believe let him speak, and towards the end we will put some questions.
Yes.
Okay.
So that his fluency is very good, interesting things will remain uncovered. Okay, madam, please go ahead.
Okay. Now we will come to the combined path detector state. That is psi equals to C1 psi 1 D1 plus C2 Psi2 D2. Here we can, what we can see, we cannot write this as a product state. We cannot just write the detector part as a product. So we take the approach to get the reduced, now we consider the reduced density matrix. Otherwise we cannot get the we cannot I mean, in the previous cases that we can write it as a product state. Now we cannot write. So the reduced density path density matrix, we trace out the detector from the combined state, and we get the reduced density matrix. Here we get the triality quantities, that is V square equals to 4C1 C2 square D1 D2 inner product square, and predictability is 1 minus 4C1 C2 square. Entanglement, or here appears an entanglement. It has become that 4C1 C2 square 1 minus D1 D2 square. What happened in the previous cases, we don't have the term, this term, and predictability remains the same. In the previous cases we see the same predictability. Here appears many conditions. When the detector are equal, what happened? When the detector are equal, we get D1 equals to D2. Then we have the visibility as 4C1 C2 square, like the previous cases. As it is equal, here this term will be 1 and the entanglement will vanish. So only the duality persists, that is V square plus P square equals to 1. Also, if you consider the like when they are orthogonal, like if D1 perpendicular to D2, so what happened? This term will be 0. We have no visibility. We only have predictability and entanglement. And at that cases, the entanglement will be 4C1 C2 square. Now we will come from this scenario when we will get the maximum entanglement in this interferometric system. So first we will consider to survive the entanglement, we should not have the D1 equals to D2. If D1 equal, already we have seen that if D1 equals to D2, we have no entanglement left. So first we consider that orthogonal cases, D2 equals to 0, the inner product. So the combined system will be for the equal, and next we consider the equal amplitude. If the C1 and C2 are equal 1 by root 2, so the two paths are equal probable. Like we cannot predict that yes, it will follow this path or this another path, because these two paths are equally probable. So at that case, we have no predictability. Predictability is 0. And already as it is the orthogonal detector, visibility is 0. So only in this scenario, we'll get the entanglement as 1. Only the entanglement left here. So this is like the maximally entangled Bell type state it becomes. So in this scenario, when we have the orthogonal detector and the equally probable amplitude, equal amplitude, equal probable predictability, at that case we'll have the maximally entangled case. Now we'll extend our we'll just verify this work in the Pauli matrix representation. If we consider the reduced qubit density matrix, the reduced qubit density matrix we can write using the Pauli spin matrices, and just simply using the expression we can get the reduced qubit density matrix in this form. And we know that is a density matrix follow this relation, trace of rho is equals to 1. Immediately we can check that rho 0, this term rho 0 will be half. So from here we also check the representation, V square equals to 4 rho 1 square rho 2 square, and P square equals to 4 rho 3 square, and epsilon square it can be written as 4 rho 0 square if I take 4 rho 0 common, and minus rho 1 square rho 2 square minus rho 3 square. So rho 1 square rho 2 square, this part is V square, and rho 3 square is the P square. So adding all this term, we will only get the term that is 4 rho 0 square. And we also already know that is rho 0 is half. For to maintain the property of the density matrix, it should be half. So in this approach, we also can confirm that it will maintain the triality relation. Now we come to the three-slit interferometer. Now we consider the pure Q-tree state. There is no entangled or combination or combined system with the detector. So we get the density matrix immediately from just outer product, and from here we get the V square and P square, the visibility and predictability, and it also follows the duality relation. There is no entanglement. As no detector is coupled, there is no entanglement. Now, again, we will consider the three-path system with the path detector correlation. Here we consider the path system and the detector system, that is C1 psi 1 D1, C2 psi 2 D2, C3 psi 3 D3. Here are three detector and three probable paths. Here is three detector, that is D1, D2, D3. Here also we reduce, we consider the reduced density matrix. We trace out the detector from the system and we'll get the reduced density matrix. Here also we get the visibility, Di, Dj's, this term, and predictability remains as it is, and also entanglement includes these detector terms. So all of them together form this triality relation. But here also comes the scenario, that is whether when visibility will be 0, same the orthogonal situation, and when D1 equals to D2 equals to D3, then only we will get the 0 entanglement. Again, we have the block representation and triality relation. Block we can also in the the qubit cases, we can also write the density matrix in a in this format using Gell-Mann basis. So from this part, we can get the V square equals to this, P square equals to this, and entanglement. This is simply the if you consider the linear entropy part, that is 1 minus trace of rho A square. You can get this equation, and adding these three, you get the complementary relation, that this triality relation holds. Next, we'll come to the in-slit interferometer. Now we'll consider the pure in-path quantum system, that is, it is not firstly coupled with the detector system. So only we will get the density matrix. I don't write the density matrix as it is a big enough. Just I write down the term, how the terms will look, and here we get the visibility as this and predictability. As this is not coupled with the detector, we will not get any entanglement. So this satisfies the standard wave particle duality relation. So indicating a pure quantum state with no entanglement. Now, again, we'll consider the quantum plus path detector joint state for an in-particle system. So as it is an in-path system, we'll have n number of detector. So that in that case, the reduced density matrix of the quantum will be in this format, and we will get the visibility, predictability, and entanglement. See here also the Di, Dj. So Ij, there are n number of detector. So if to get the 0 entanglement, all of them should be equal. At that scenario only, if D1 equals to D2 until Dn, at that scenario only we will get the no entanglement. And also if all detector are orthogonal. If all detector are orthogonal, then we will not have the visibility. Otherwise, there are chances to get visibility and entanglement. Now this is the how they're connected. Just I make a graphical representation. Now we'll come to the noisy models. We investigate the effect of environmental noise in noisy channels. Like we consider here 3 channels. One is amplitude damping, another is phase damping, another is non-Markovian amplitude damping. What is our goal here? To test whether the triality relation survives under noise. First, we consider the amplitude damping. Here are the two Krauss operators, and this is how the state evolves. Like the damped state will be look like that. This is the normal reduced density matrix, and after evolution, this is how it evolves, and the resulting density matrix will look like that. So this is the physical effect, how the parameters are changing. That is v prime square 1 minus gamma a v square. This is changing. Predictability changes, entanglement also changes. So this is, if we add them three, also we'll get the triality relation. They are, so what that does it imply? Visibility changes, predictability changes, and entanglement all are changing, but they are keeping the triality relation. That means the system is redistributing their information, or everything is redistributed among themselves. So there is one example. First, we take the pure equal superposition. This is a single qubit state. This is not attached to the detector. Like for qubit cases, we express like in the previous cases, that is C1 psi 1, C2 psi 2. Here, what is? Here the expression is 1 by root 2 0 plus 1. 0 is the common computational basis. 0 is 1 0 and 1 is 0 1. So as it is not coupled to the detector, the initial values is the v square equals to 1. There is no predictability, as it is the we can see that equal probable, so no predictability, and entanglement is obviously 0. So what we get after amplitude damping with parameter gamma, this is a evolved density matrix, and now we get the triality 1 minus gamma p square equals to gamma square, and entanglement square is gamma minus gamma square. What happened? That is, visibility is decreasing and predictability is gaining. And what happened to entanglement? Entanglement is decreasing, and first it is increasing, after that it again comes to 0. So this see the plot here, visibility is coming 1 to 0. This is simply 1 minus gamma. Gamma is, when gamma is 1, it will be 0. And what happened to entanglement? For the predictability it is coming from 0 to 1, because gamma is 1 maximum value, so predictability is 1. And for entanglement, what happens? From 0 to after a certain point, from it reaches to the maximum value of 0.25 when gamma is 0.5. After that, it starts to again decrease, and when gamma is equals to 1, it becomes again 0. So the initial state and origin of entanglement. First, we can consider this is what I told already. This is the state, and this is how the density matrix. And when the unitary system environment process, when the coupled system is the noise is applied, the system and environment superposition will get this combined system. This state is not a separable state. Hence, amplitude damping generates system environment entanglement. Now, this is already I discussed. That is, this is what is the maximum value. This is 1/4, and when the maximum entanglement in this case occurs, this is 1 by 2. At gamma equals to half, we will get the maximum concurrence. Here we will get the maximally entangled state. We don't get, because it is already in a damped situation, and already it has no entanglement stored. So after that, we'll come to the phase damping. Phase damping, here we are giving the example of qubit cases already. Now, after that, we'll discuss the qubit cases. So here, what we see, that the density after the evolution, the density matrix looks like. Here we see that visibility changes, but predictability remains as it is, and entanglement is redistributed. And also here the triality holds. Now the scenario is same density matrix, same state. What happened? Initially the v square equals to 1, p square 0, and e square entanglement square is 0. So here the triality becomes B square equals to 1 minus gamma, P square 0, because for phase damping, there is no change in the predictability, and entanglement is gamma P. This is simply that when visibility is 1, entanglement 1, 0, and when visibility is 0, entanglement 1. That is the entire there is a the information is redistributed, and the properties like visibility is decreasing, and this the visibility stored as information in entanglement. They are just redistributed among themselves. Now we'll come to the non-Markovian cases. Here we see that is here that memory effect comes into the play, and here is a time. There is a like time dependency or time evolution is going on. So we have the reduced density matrix, and we'll have the distribution like this b prime square as this p prime square in this format, and entanglement square. Here we see the some interesting fact, that is see, we consider the same state, and here see, this is entanglement. Entanglement is increasing, after again it comes to the 0, again it comes to some certain value, again 0, again some value. After that, after some certain time, it becomes 0. So there is some revival of entanglement, sudden death and revival. Similarly, also we see the visibility is 0, visibility again revives. There is like revival of visibility also, and predictability after a certain time it goes to the maximum. It is 1 when both visibility and entanglement are 0. Now, same situation we are observing for the Q-treat cases. For the Q-treat noisy channels, Q-treat state under noise, this is the maximum coherent Q-treat state, like 1 by root 3, 0, 1, 2. This is the single Q-treat case. And here also we see that at first the entanglement 0, and after certain values it comes to the certain maximum values for these cases, and again 0. Predictability is increasing and visibility decreasing. Same for the phase damping cases, predictability does not change, it remains 0 all along. Entanglement and visibility redistributes among themselves. Similar situation arises for the non-Markovian cases. Non-Markovian cases, we also here also we see the redistribution, also the revival, partial revival of the entanglement and partial revival of the visibility, while predictability after a certain time becomes saturated to 1, and both visibility and entanglement comes to 0. So this is our key result. Triality relations verified for qubit, Q-treat, and general n-dimensional system, and these triality relation valid under different noisy channels: amplitude damping, phase damping, non-Markovian dynamics, and environmental noise redistribute visibility, predictability, and entanglement, but does not violate complementarity. These are the reference we are following. Thank you.
Thank you, Dr. Ramita. Is there any question from audience?
Thank you. This is very interesting talk. I have some couple of questions. My first question is, you represented that like it's a common thing. Let's say if my system have E square is equal to 1, then V and P become 0. So what kind of system it is? Let's say we know that coherence represent the quantumness of the system. So if coherence is 0, that means it's classical, but this has entanglement, maximally entanglement. So this system is what kind of system? So,
not coherence. There are also many states that show coherence is 0, but they are entangled. Not likely that coherence always not equals to 1 represent the coherence equals to 0 represent the classical cases. There are also many cases that is coherence is 0. So
and my second question is, you represent when
just want to give one example. So, Ramita, one example would be the 2x2 case which you took. Pure mixed state. Pure mixed state.
yeah, sir.
Sir, your
Yes.
voice is not clearly coming.
Pure
Okay.
mixed state.
Pure mixed state. Yeah, sir.
For that,
And
P is equal to 0, P is equal to 0.
yeah. Yeah, sir. This is like the maximum coherent cases I considered, but this is not entangled. And like this is not the scenario always that when we get the like there are many quantum there are not separable state. There are many separable state that have their in coherence value, but they are not entanglement. Vice versa, there are very like GHG state has less coherence than many other entangled state. So as it for 3-qubit cases, GHG we know the GHG the maximally entangled state. So this is not like the coherence is a measure of like non-classicality.
Got it. My second question is like you saw that epsilon naught bar like E bar is like when you put the amplitude damping channel. So let's say I have 2-qubit system and environment. In that case, this E prime, what it is represent? It is represent the entanglement between two system, or it is represent entanglement between system and environment, or the mix of them.
Okay. This is like first if we consider here is an interesting key, that is when I consider in the example cases there is no detector. So as there is no detector, there is no entanglement between the detector and path system. So here in the example cases, entanglement is the between the system and the surroundings. But when the detector comes into the play, here there are two kind of entanglement is included. One is detector system entanglement, another is system and surroundings entanglement. Two entanglement are embedded.
I see. Is there any way we can find out how much is one and how much is another one?
Yeah, that can be you can find out because this is here I involve the linear entropy or the I concurrence measure. If you use the other measures, that is simply detector path entanglement, they will not they will cut down the entanglement or correlation between the path and the environment. Then only you can get the uh, different measure, like this is for this part, this is for another part. You can differentiate.
I see. Got it. Thank you for the information.
Madam, actually, this paper is very interesting. And first thing is that
Thank you, sir.
share this paper, and it really goes to the foundation. But it is
Okay,
lot
sir.
of actually previously we know probability only, but now we have predictability. Newton. Predictability high means probability is low. Am I correct? High predictability
actually
means particle nature. Probability is low. They are reciprocal.
Actually, yeah, but I mean the exact like if equally probable, like if you get that two path here, suppose we consider two path.
If equally probable,
then the
then
predictability is
how
zero.
predictability is zero? Because if it is equally probable, if it is 1 by root 2, C1 mod C2 mod is equal to 1 by root 2, and both the paths are equal probable. That means you don't know which path the particle travels.
Yes,
so
exactly.
How do you say the predictability is zero? Unless C1 is zero, only one path. If you say these are some confusing, but time is very less. You my request is you just send this slide and we will find very much interesting. We have know what to express the now.
Okay, sir. I am explaining. When there is no the equal, when the two paths are equal probable, you cannot say something about the path, like whether the quantum will follow path 1
This
or path 2.
part 2.
So there is no, you have no information about the which path it is going to follow. At that case, the predictability is 0. But if it is like 60-40, like 60%, it can follow it can have the probability to go in the 60% to this path 1,
40%,
and path
then
2
probability
40%. Then the probability is not is not equal. Then you can have the information. Yes, it is most probably following path 1.
This path.
This is like predictability is connected.
Yes. I get it. Anyway, but very. You send the organizer. I appeal to the organizer or collective or slide. And
okay, sir. I will send.
Okay.
Very nice talk, Mr. Ramita. It's a very interesting topic, as Professor Tony said. Please do share your slides with the organizer. And also, if you could share some of the reference articles related to this topic. Yes,
okay. I'll share my paper also, and also the previous paper Sir has done with Abhinash, Nitish, and Professor Qureshi, and Qureshi's optics latest paper. I'll share.
Good, because it presented very good, and we are excited to this is a very interesting topic. So please help us so that we can also contribute something in this way. Okay, thank you.
So diagonal metrics are the pure state, I believe. Off diagonal are the entangled state. Is it correct?
Not like so, sir. Not like so. Like this is for these cases, for our cases, this is like the reduced system I consider. This is not not entangled. The diagonal element, there are some like states that have that only the diagonal elements, but they are entangled. Like if you consider like Bell state, suppose Bell state is a maximally entangled, but if you take the reduced density matrix, so that actually I mean mixed pure, you can say that about that, but
mixed pure state and mixed state. Yeah, you can say mixed state. 3 1 2 3 diagonal mane 1 1 2 2 3 3 pure state. And off diagonal means 1 3 mixed state. You can say mixed state, not entangled state.
Yeah.
Yes. I got it.
I have one question. So thank you for a very interesting and informative talk. In which quantum problems one can apply theory discussed and developed by you in your presentation? Do you have any idea?
Actually, I had seen one paper. They have developed for single qubit system. Like they calculated some about some quantum correlation or quantum, not in this format but different format. They have some single qubit cases with passing through the. If I get the paper, I will share. In the optical system, and also say like interferometric system. I could not remember properly. If I get, I'll let you know. I'll send you.
Like the reason one generating new state using nonlinear crystal. Okay, so these things are very useful. Okay, preparing new state using like structural light. So these things can be exploited there. So I will share a couple of papers with the professor who asked this question.
Okay, sure. Thank you.
It is highly useful.